show you guys, we're going to do a lab, for those who have lab this afternoon, we're going to be doing the laser beam collimation lab. So I have a demo video that I put together that I think will be helpful for everybody to see. Back when I was young. So we're finished with everything up to chapter 6, right? 6 or 5? 5. 5, chapter 5. And so the exam, actually let's point it out now, before I forget. This exam covers pretty much everything, 10 questions, everything from chapter 1 to chapter 5, except for chapter 3 because we jumped over that one. So basically there's a problem in laser safety, there's one on characteristics of light, calculate wavelength frequency. These are nothing that you haven't seen before, so this is kind of more of a review exam than anything else. Question about dispersion, a Snell's law problem, a photometry problem, a diopter problem, let's see, thick lens, I mean a lens maker's equation, thin lens, and a concave mirror. On the top here it says, on a separate sheet of paper, please don't try to solve the problem right in here because my eyes are getting old, I don't have readers yet, so separate sheet of paper, that way I can follow it and you'll have plenty of space to write, you know, be creative and neat. Always show your equations that you're using so I can follow it. So if you get it wrong, at least I can find out where you got it wrong and give you credit for it. Also, and I can't stress this enough, always, always, always show your units, whether it's centimeters, microns, watts, milliwatts, always show your units. Because if you get everything right and you write, you know, x equals 8, I don't know what that means. You know, wavelength is 400. 400 what? Angstroms, millimeters. So it's all about precision. For those of you who just came in, field trip sign-up sheet for tomorrow. Okay. If you have any interest in laser cutting, welding, drilling, cool kinds of laser stuff, applications, go. We leave at 9:30 tomorrow morning. Tours from 10 to 12 at Arcor, which is in Suffield, Connecticut, right by the airport. We'll be back here by 12:30-ish. So if you haven't signed up, if you're interested in going, it's a fun trip. They're always fun. They're so happy to bring us down there. They're all excited for us being there. Probably good donuts. This is a company that wants to start a formal internship program with us, so if that's in your wheelhouse, it's a good thing to have. To inform yourself. Arm yourself with knowledge. All right, so let me go through the last thing. Has anybody looked at this video yet? Anybody visit? I guess I should check the stats on the Blackboard site to see who's visiting and who's not. I can do that. Okay, if we go to homework and lab assignments, Chapter 5, there is a video demonstration, laser beam collimation. Work, please. Nick, help me. YouTube is not working. Don't know why.
Huh.
You know what? Maybe I gotta research it. Laser.
Odd.
That's when something got removed.
That's, yeah, that usually comes up when something gets removed.
Yeah.
You just want to put this on your phone?
Yeah, no, that's not mine though.
Huh.
That means
Yeah, maybe it's gone.
Is it on your account or on?
in the combination Laser Geeks. There it is.
Okay.
We have this whole series called the Laser Geeks.
In this experiment, we will calculate airspeed using the auto-collimation method. Now, this experiment uses three basic components. We have here a microscope objective mounted on a microscope objective holder, mounted on a 3-inch post-and-post holder. I have a 2-inch post-and-post holder that is holding a bar-type lens holder. I also have this mounted on a base platform here. And what I've done is I've taken an index card and I've taped it to the bar-type lens holder, and I've drawn myself a target that is geometrically centered along the axis of the post holder. I also have a biconvex lens, the focal length of which I am unsure, and as part of the lab we're going to try to kind of figure that out. But basically what we're going to do with this lens is collimate the laser beam. Now, most lenses used for this application, at least with regard to your kit, are in the 10 to 20 centimeter focal length range, and I'm thinking that's probably what this lens actually is also. And I have it mounted in here, basically using the V groove like that, and the second V groove on top applying a little pressure to it. Okay, so the first thing we want to do, if we can just pan back a little bit, is level our laser beam. Usually in most of these experiments, it's always good to start off with a leveled laser beam. And what I have is a helium neon laser. I'm going to turn it on. Okay, and what I want to do is make sure that the laser is level in the horizontal axis, and it's also aligned in this axis here, and I'm going to use the screw holes as a guide. And what I'm going to do is I'm going to check the level here with a ruler, and we're about 5 1/4 inches here, and if I go down to the other side of the breadboard, we're about 5 1/4 also, so this is fairly level to start off with. Now, one of the things I want to do is, using my index card, notice how the laser beam is centered on the crosshair, okay? And I want to keep it that way, okay? So as I move this crosshair, I'm going to tilt it slightly. As I move the crosshair across the table, I just want to make sure that the position of that beam doesn't change, and in this situation, it really doesn't. If it does, okay, what I want to do is make sure that I adjust the position of this laser in this direction here so that it is centered on that crosshair. Okay? And just to secure that target, I'm going to take a 1/4-20 set screw and just kind of tighten this down, because we're going to use this target as we're doing the auto-collimation process. Now, given that this laser beam is aligned in this direction, the next thing I want to do is expand it. Okay? Part of the reason for expanding and collimating the laser beam is that the larger a beam is, the diameter of that beam, the farther that beam will travel without diverging, or divergence is directly proportional to the amount of collimation of that laser beam. So the more collimated or more parallel a laser beam is, the less it will tend to spread out over a certain distance. Also, the larger you expand the beam, the less it will spread out. That also has implications with regard to materials processing, for example. When you try to focus a laser beam down to a small spot, the more collimated and larger a beam is, the smaller the focus spot size will be. So just keep that in mind as we're doing this. Now, what I want to do is take this microscope objective and bolt it to the breadboard, and we're going to use this to expand the beam. Now, the fact that we've fixed the target, okay, we want the expanded laser beam to be centered on that target. Okay, so what I'm going to do, if you can see the target over there, I'm just going to adjust the position both in the X and Y direction so that it sits right centered with the target. Okay, so right there we look like we're fairly centered, and that's good. Now, the next step is to take your your biconvex lens and place it somewhere in front of in between the microscope objective and the target. And what we want to do, if it hasn't already been aligned, okay, if you do this, you might be off axis a little bit like that. Okay, you can see that we're not quite centered there. What we want to do is center the post and post holder over these screws, the screw holes, and adjust the height of the lens so that we are centered. Okay, so right now we're centered. We are centered, the laser beam is expanding, okay, and it's being collected by this positive lens, and it's actually collimating to some extent that light. Okay. The thing that we don't know is, how well is that laser collimated? Because if I just take this off and I move it, okay, notice how the beam, as I move away, expands. Okay, so the beam started out that size and ends up over here being expanded. Now if I adjust the position of this second lens, I can make that spot bigger or smaller. And one way to determine, or the way to make sure that this beam stays the same diameter, regardless of the distance away that we are, is by using a technique called autocollimation. Now, what happens in autocollimation is that if the back focal length of the collimating lens coincides with the front focal point of the expanding lens, then that beam will be collimated. So what we're going to do to check that out is we're going to take our target, and what I'm going to do is I'm going to position it about 8 millimeters just off axis, about 8 millimeters in front of the microscope objective. Okay, so this plane is co-aligned with the focal point of that lens. Okay, and what I'm going to use that for is to reflect the light back, which is the principle of autocollimation. Okay, now what we're going to do is we're going to take our plane mirror and we're going to use it to reflect the light coming through the lens back just off axis. And if you can zoom into this here, you can see the spot there. Okay, we're going to zoom it right off axis there, and we're going to look at the size of this spot as we adjust the position of the collimating lens. So if you pan back just a little bit to catch the collimating lens, okay, that's good. What I'm going to do is adjust the position of the collimating lens and find the point at which that focus spot reaches, is basically as sharp as possible. And we look like we have it about there. If I go a little bit farther, it starts to expand again. If I come back this way, it starts to expand again. So what I want to do is find a spot at which the reflected light just comes to a point off axis. And what's happening here is the light, as it's being expanded by the microscope objective, is spreading out, coming through the lens, being collimated. It ends retracing its steps, basically, and if we can get it to coincide with the focal point of the microscope objective, then we should be fairly collimated. Okay? And again, you want to make sure that you are aligned with the axis of the screws here. What I'm going to do is I'm just going to bolt this down at the position that I just determined, hopefully, is the right spot for collimation. And what we're going to do is we're going to check that collimation just by doing a visual inspection of the light as it travels from the laser. So as we can see, the laser beam starts out probably about 1.5 millimeters in diameter. And by using the microscope objective, we're able to expand that beam out to a larger spot, and then we're going to collimate that again. And what we're going to see as I move this away is that the beam diameter is not going to change. The farther I go, it still stays relatively the same diameter. Okay? That is a collimated beam.
gonna
Pretty-
autoplay.
Oh, yes. Focal length. All right, so if you do, if you're interested, I think there's 25 of these videos on, just look for Laser Geeks on YouTube, and we have a whole series of a bunch of different experiments, anywhere from diffraction, Young's double slit, to single and multiple lens systems. They're actually pretty useful. Most of the labs that we have are based on this series that we did a while back. That was when was that? Maybe like 99, 2000. That was about 15, 16 years ago. Back when I was younger. Didn't have gray hair. So what I wanted to do today, so we're finished with chapters 5 through, chapter 5, 1 through 5. Before we jump into the next section, I think I want to spend just a little bit of time explaining what we're going to be doing in the lab. It's actually kind of interesting. You're going to be doing that, but it's a modified version of that. You're not going to be using just a microscope objective. You're going to be using a device called a spatial filter. A spatial filter is essentially a microscope objective with a pinhole filter attached to it. This is a commercially available beam expander spatial filter / collimator. Okay, you see this interesting looking device at the end here. What this thing is a very expensive focusing lens. Basically, it has a microscope objective, just like you saw in the video, but it also has attached to it a 3-axis micrometer that is used to position a very small pinhole right at the focal point of that lens. And I'll explain why that's important in a second. But basically, what happens is you take a laser beam, you shine it into here. This microscope objective expands the beam out, and it's collected by this larger biconvex lens. And the position of this is set at Newport Corporation, and precisely so that it will collimate that beam as it comes through. So if I just kind of sketch what this looks like on the board, okay, I think you'll get the idea. So you start off with a laser, okay, and the first thing you go through is that microscope objective. So the microscope objective is nothing but a very small, short focal length lens, sometimes called a fast lens because the focal length, it comes to focus really fast. And what that does is it'll expand the laser out like this, okay? So, because you want to spread the beam out to make it bigger. So, and again, this focal length is very short. The ones we have are usually about 3-4 millimeters, depending on whether you have a 10x or a 20x lens. So this is the focal length, we'll call that f1. Okay. The second lens is usually a larger lens, obviously because you want to expand the beam and collect the light. Okay, so when the light strikes this, okay, if this focal point, the focal point of this lens, corresponds to the focal length, focal point of that, so this focal point of this bigger lens coincides with the focal point of the smaller lens, okay, we call this f2, then this beam coming out of here will be collimated, okay? And you'll find that if you have the diameter going in, okay, diameter going out, diameter 2, these two are proportional, okay? The longer the focal length, the more it's going to spread out, the larger the beam is going to be. This is the trick, okay? So if you were setting it up like I did in the lab there, where you don't have any reference point, all you really need is like an index card, like I showed. And what I was doing in that video is I put an index card just off axis, right at this focal point, all right? So, and then I took a mirror and I put it over here, okay? If this beam is perfectly collimated, you know, it's perfectly straight, then what will happen is when you reflect it off of a flat mirror, that beam will retrace its path, okay? And if you just put a little bit of a tilt into this so it comes off axis, this should come right back to focus just off axis because you're tilting it right at that card. Now, if this position of this lens is not accurate, off a little bit this way, if it's off a little bit that way. If it's a little short, what's going to happen to the beam as it goes out?
It's gonna expand.
It's going to expand. So if this is a little short, okay, this beam is going to go like this. And if it goes like that, and you reflect it back, okay, it's actually going to come to focus closer. Okay, so in this thing, the opposite is true. But if this lens is a little bit too far, okay, then your beam is actually going to start converging a little bit. And if it converges, it's going to come to focus at a spot that's not where it's supposed to be. Okay, so it's only at that point where these two focal points are perfectly aligned that you get a collimated beam. Now, in the video, I just did it by eye. I mean, if that's all you have, you know, you can set the system up. You know, if you have a long enough space, you can walk across the room and measure the diameter here, measure the diameter over there, you know, tweak it back and forth just a little bit just to make sure that it's perfectly collimated, okay? And that's actually a pretty accurate way to do it. However, we have better tools for that. These are what we're going to be using in the lab today. These are called shear plate interferometers. And I couldn't think of a better way to launch us into wave optics than to use a shear plate interferometer. Now, a shear plate interferometer, I'll pass this around. And by the way, before I start, you know how much this thing costs? Optics is crazy. Now, this one's about $2 grand. It's not that. I have bigger ones that are more expensive. But I mean, just this part alone, and you're going to be using one of these. We have these without the lenses attached to it. Just these, you know, you go to the Newport catalog. These are about $900 for just this little mount. Okay, so they're not cheap. This is from a company called Mel's Brio, which is down in Stamford, Connecticut, I believe. And what this has is a cube. I believe, if I'm right, this was actually designed by an undergraduate student at the University of Laverne in California and marketed after that as a product. It was a senior project, I think. But it's, if you look inside there, there's a hole. Inside of here, there's a highly polished piece of glass. Now, when we talk about highly polished optical flats, the flat piece of glass, you know, remember what we said. What does it mean when you say something is optically flat? Everybody at once. Don't be shy.
Absorption.
When we say optically flat, we're talking like geometric tolerances. Okay, how flat is flat? How do you define flat? Yeah. How much variation from flat is it? So these are usually perfectly ground, not perfectly, but ground optically flat, usually to within a 20th of a wave. Which means over the diameter of this flat piece of glass, the surface doesn't change by more than 1/20th of a wavelength of light. It's very flat. Okay, and we test those with laser light, so we'll actually do that. But inside here, so this thing is mounted at 45 degrees. So when light comes in, you basically have a piece of glass that's mounted at 45 degrees. Light comes in, what's going to happen? You're going to get reflected, right? So you get a collimated beam, hopefully, coming into this thing. Reflects off the first surface. How much reflection do we get off the first surface?
96%. We lose 4%.
Well, the 4% is what we get. Yeah, 96% goes through. So we get 4% reflection, so that actually comes and goes in that direction. The rest of the light goes through, but as it's going through the glass, you get the back surface. And again, you're going from glass to air, you get a change in index of refraction. Whenever you have a change in index of refraction, you also always get a reflection. So you get another 4% reflection. So now you get two beams traveling pretty much in the same direction, overlapping probably by like 95%. But you have two beams traveling in the same direction. Because we're using laser light, and again, this is when we get into coherence properties of lasers in wave optics. But if you have coherent light, what coherent means is that light, okay, if you take a sheet of light, if you do a cross-section of it, means that all of the little waves of light are all traveling in lockstep with one another. They're not varying with respect to one another. Every little beam is traveling exactly the same, little waves traveling the same direction, like a marching band, okay? And if there is, if you look at the beam reflecting off the front surface compared to the back surface, if that beam came in and it was not perfectly collimated, okay, as the light goes through and reflects off the back surface, light hitting certain parts of the back surface when it comes back up are going to travel a slight distance farther than the light from the front surface. Okay? In the the divergence of the beam, how much the beam spreads out, dictates the orientation of what are called fringe patterns. Okay? So on the top part of this, okay, light's coming in, you have this little screen. Okay? And the little screen has a little crosshair on it. And what you hope to see when you pass this light through this cube, I'm going to draw it up here. If you're looking down at this, okay, light's coming, after you remove this mirror, light goes into this thing. You're going to see this screen with a line. You're going to see fringes, interference fringes, which are actually a tool. When we talk about, precise laser measurement, precise laser measurement is based on the interference of light. When light is coherent with itself, okay, the beams are all traveling in lockstep, you can actually, if you shift the phase of one of those beams relative to the other, where one's going up, one's going down, okay, you can actually cause destructive interference. Light can cancel itself out. Conversely, if both the beams are traveling in the same direction at the same time, they're going to add together. And the result of that is going to be something that looks like this, a fringe pattern. So when we talk about fringe patterns, we're talking about these lines that are bright, dark, bright, dark, bright, dark, bright, dark. Whenever the light arrives at that screen in phase, you get a bright spot. Whenever it arrives out of phase, you get a dark spot. But the orientation of this will tell you whether that beam is collimated. Only when the beam is perfectly collimated will these fringes line up with this line. So you set up your optical system, okay, auto-collimate it, try to align it as best you can by eye using auto-collimation, and when you think you're there, you just take that little cube, put it on a post, put it in front of your beam, and then you look at the pattern. And then you tweak the position of this mirror back and forth, and what you'll see that as you tweak that position of that mirror back and forth, these lines are going to go in either direction like this, and you just find the position where they line up with that crosshair. And when you line up with that crosshair, you're done. That beam is perfect, as collimated as you're going to get it. Now, so that's one part. The other part of this is spatial filtering. What I did in the video was basically taking a raw laser beam, expanding it, and collimating it. The problem with that is that that's not the best possible quality beam that you can get. If you're doing this, the purpose of expanding and collimating a beam in a lot of applications is to get a nice, clean, larger diameter laser beam that is uniform in intensity and phase across that cross-section, because you're going to use that in an interferometer, in a very precise measurement tool for testing optics. You have to have that clean. You can't have interference fringes, noise basically, in your beam. So if this is all I did, even though it might be collimated, when you look at that expanded beam, it's nice and collimated, but you're going to get stuff that looks like this. You're not going to get a nice uniform disk of light that's nice and just one spot of red. It's going to have all these little squiggly lines and stuff. And why is that?
Particles in the air.
Particles, not so much in the air, but on this laser you've got a window here.
Yeah.
On the lens you may have a scratch, a dust particle, something. Small objects, scratches, dust, any particulate matter that gets on your optics. This is the whole subject of wave optics, is when light passes over very small things, it diffracts, it bends, okay? It goes out, it interferes. So any dirt or scratches or aberrations in those lenses are going to cause a laser beam that's going to look like this. And the reason is all of that light that's being focused down onto the spot, the scattered light, diffracted light, actually comes to focus off-axis. Okay? It goes this way, it goes that way, and it results in something that looks like this. So if at this point here, if I took a very small opening, okay, a little filter, basically think of it as like a washer with a hole in it. That hole is about a quarter of the diameter of your hair. Okay, the one I'm going to show you is 25 microns. Okay, this hole is 25 microns. Okay, the light that goes to the center of that, okay, is what we call DC light. DC, like direct current. It's analogous to DC voltage, where it's not changing, it's not being modulated by anything. So DC light is called pure light. Okay, it's clean light. And anything that's off axis is what we call modulated light or dirty light. We want to block out the dirty light because that's going to cause this stuff in my laser beam at the end. Okay? And the only way to do that is to very accurately position this hole in this direction, and in this direction, three axes, a tiny, tiny hole with the focal point of that lens.
So why is it adjustable? Why isn't it set when you get it?
Because when your laser beam comes into this, you can never hit it the same twice. So if you line this thing up, and then even if you turn don't move anything, you turn the laser beam back on, just the laser, because as it heats up, the optics kind of change and the direction changes slightly. It's not going to be lined up directly with the pinhole. When I talk about the pinholes, this, by the way, is a pinhole. Okay, I'll pass this around. These things are not cheap either. These are like $150 a piece. But you're going to look at this and you're like, where's the hole? You hold it up to the light. Just look at it and see it. Yeah, I mean, they're so small that you can't even see it unless you shine a laser through it. But this device has a magnetic mount. These micrometers, the tongs on these are metallic, they're magnetic. So that, when I put it in here, it'll stick to this, and then I can position the thing up this way and this way, just to get that one point. It's not as easy as it looks, right, Dave? People get frustrated with how the heck there's actually techniques that you can do it really quickly. And I'll show you those techniques in lab today. But this is why laser techs get paid money, because they have the patience and the skill to be able to align these systems to a certain degree of accuracy and do that repeatedly. So this is the shear plate interferometer. Okay, that's the pinhole I'm passing around. Again, when we go into the lab, you're going to get this part of this device. Okay, and you're just going to mount that on a post and try to align it using the same methods we talked about. But a lot of times, if you're just aligning an optical system without a laser, and you want to make sure that things are properly aligned. Remember the auto-collimation method that I just showed you? Well, there are devices called better phone, I guess. We have devices called autocollimators. This part hooks up to a light source over here. But this device essentially has a microscope objective. It has a light beam that's collimated and it shoots out, reflects off an optic, comes back, and then is directed upwards. And there's a little crosshair target if you look at it with light going into it. Let's see. Okay. There's a crosshair target that if you're trying to align a flat optic to this, okay, if it's perfectly lined up, you'll hit that crosshair right in the center because it takes the light, expands it, collimates it, brings it back, and it brings it right to focus. So you get this little point of light that sits on the crosshair. So this, again, is just a tool that's used in the optics field for doing optical alignment. I thought this would have been a really cool demonstration because the people who were supposed to come today and talk, where they went, so they're okay. This is what they do. L3 Communications makes not satellites, but telescopes, basically. Beam directing systems. If you ever think about like a spy satellite, basically it's a telescope, reflecting telescope that's turned the other way, so you can focus on images on the ground. Those optics have to be perfectly ground tested. They also do this in the infrared and the ultraviolet, so you have to have, understand, how that light works. So this company, this is what they do. They hire our grads to go work on these very sophisticated, usually defense-related projects. And they're looking for a few good people. They're out in Wilmington, Mass, off 495. It's actually a pretty big company. Big defense contractor anyway. They also have divisions in, in New Hampshire, You guys remember Cole Morgan in Northampton, Mass?
Yeah.
Yeah, Cole Morgan is now L3, they're up in Deerfield now, but that's one of their, I think they make the periscopes for submarines there. They also have a company, a division called Insight, which is up in New Hampshire. Insight makes the lasers for military, for guns, sighting, laser weaponry, that cool stuff. What do you think? Anything else? In the time that I have remaining, I'm going to demonstrate to you, I'm going to build a little system real quick just to show you what a dirty laser beam and what a clean laser beam looks like. And then that's going to be your job in lab today, to build a laser beam expander collimator that is spatially filtered using a little pinhole filter, and then measure the diameter of your beam, and then figure out, okay, so I expanded this beam, how big will that beam be if I shoot it at the moon? How much will it expand? Because no matter how good your beam is, how big it is, it's still going to expand a little bit. So if I took a beam, let's say it's this big, if I use this device here, this beam, how big do you think that's going to be if I shot it at the moon? If I started here, shot this thing, it's like this big in diameter, shined it up to the moon, how big do you think? 250,000 miles of travel.
We should do this.
Mile and a half, so.
Yeah, that's about right. If I didn't expand it, I just used a regular laser beam, which is like 1 or 2 millimeters in diameter. If I shot that at the moon, how much would that expand? How big would it be on the moon?
Not the same.
Couple inches.
A couple inches. His was a mile. Remember, the bigger the beam, the less it's going to spread. So if a beam is like this big in diameter and it ends up being a mile wide on the moon, if the beam is like a lot smaller than that, smaller beams diffract more, not diffract, but diverge more.
All right, well,
Okay.
I'm betting
So we're talking-
2 moons in diameter.
Maybe not 2 moons, but we're talking probably about 100 miles or so. Okay.
That's a solid guess.
Well, that's why I wanted, sometimes you got to predict these things. So there's, like everything else in life, there is an equation that dictates what that is. And this is one of the questions that you're going to be asked in the lab today. So if you have a laser beam of a certain diameter, okay, the divergence of that beam, it's just an angle. Okay, so you start off with a beam that is a certain size, this big. How big will that beam get over a distance? You guys did this for laser safety, remember?
Yeah.
Okay, so over 1,500 feet, how big, do you remember what the number was?
30 centimeters?
30 centimeters or so. So, 30 centimeters starting off as a millimeter, that one, because it's so small, actually had a pretty decent divergence. But this is what we mean by the divergence angle. How much is this beam going to spread over distance? Okay? There's an equation for that. For a Gaussian beam, and I know we haven't gone over Gaussian beams yet, the laser beams have a Gaussian shape. Okay? The intensity distribution looks like a bell curve. Okay? This is the best beam, the best shape that you can get for expanding and collimating a beam. Its divergence, there's an equation for it. It's 1.27 times lambda over d. There's only 2 things that determine what that divergence number is going to be. Okay, 1.27 lambda over d. So if you have a longer wavelength, it's going to have a greater divergence. If you have a shorter wavelength, that divergence angle is going to be smaller. On the other hand, sometimes you're limited to what wavelength you're using. Diameter. The bigger the diameter, the smaller the divergence. The smaller diameter, the bigger the divergence. Okay. Now this is actually in radians. Okay. If I want to convert this number in radians, if I want to convert this to degrees, okay, how would I do that? How many radians in a degree?
360?
Yeah. Or there's pi radians for 180 degrees. So if I want to convert this to degrees, remember the conversion method? Okay. If I'm looking for degrees, I put degrees on top. So I just multiply this by 180 degrees per pi radians. Okay. So if I take this part, which is the divergence in radians, and just convert it to degrees, then you can well, you can do it with radians too, but most people are used to working in degrees. Then you can use that to figure out, how big is this going to be over a certain distance by using the tangent function. In this example, the radians would cancel out the radians here and it leaves you with degrees. On the other hand, if you want to figure out, and we use the same equation to calculate how small that laser beam can be focused. Okay? If we're looking for lasers for spot size. Okay? Spot size is what we call that little d. And so if you take that laser beam that's collimated and you want to focus that to the smallest possible size, okay, there's a couple things you have to consider. First, how big is the beam initially? That's the diameter. And then two, what's the focal length of the lens, assuming it's a perfect lens. God made the lens. The focal length and the wavelength comes into play. So the spot size is equal to that same thing, the divergence, okay, in radians times the focal length of the lens. Pretty simple equation. Okay? If I plug that divergence number into this, that spot size can be expressed as 1.27 times lambda over d, okay, times the focal length. Okay? And you look at that and you go, oh God, not another equation. Equations, equations, equations. Okay? But the equations help you to model physical systems. If I look at that equation and I want to make that spot smaller, why? Why would I want to make a spot smaller? Remember irradiance? Okay? If I want to increase the irradiance, increase the power per unit area of that spot so I can drill holes and stuff, okay? The smaller the spot, the more energy is concentrated in that spot. So if I want to make D smaller, what parameters do I have to mess around with?
The wavelength and the diameter.
I can make the wavelength shorter, which is why Blu-ray can do HD versus regular DVD. Okay, smaller spots, more data on the same size DVD. I can make a shorter focal length. Okay, if I want to make that spot smaller. But if you make a shorter focal length, what happens? You have a faster lens. Okay, the faster it converges, the faster it diverges. So you have less of a what's called the Rayleigh range, depth of field. So if you're trying to do marking and etching on a surface, and you need to have a high energy density, power density, just on the surface, use a shorter focal length lens. If you need to drill a hole in something that's deeper, or do some deep penetration welding with a laser, you probably want to use a little longer focal length lens so that it converges less, so you have more room for that beam when it comes down to that small spot, more room, flexibility in where to position your part. The other thing is D, the diameter. You want to make a very small spot, make a very big beam. Okay, you increase the diameter, which is why we're doing what we're doing. Okay, that allows you to focus it smaller. So depending on what you're trying to do, whether it's materials processing, you want to make very small spots, with a laser, expand the beam. If you want to send the beam, to do, time of flight measurements or laser radar, then you want to expand the beam so that it doesn't diverge. And if we're trying to shoot this beam at the moon, okay, why do we do that? I mean, why do we want this to not expand?
Want to be able to see it.
Yeah, you won't be able to see it. If it expands too much, you don't have any energy. And if we put a retroflector, a mirror on the moon, the idea is to take part of this beam, shoot it up there, reflect it back, from that mirror, so that you're able to measure it. Okay, how long does it take for the light to come back? You have to have enough energy to get back, to be detected. So the less the divergence of the beam, the more energy you're going to have in the return signal, the easier this is detected. Right? Makes sense? Good? Everybody's nodding their head, that's good. All right, so size matters. Now, let me just give you a couple minutes. I just want to show you what this looks like. I would use this one, but I need a special mount to mount the laser if I'm using that particular device because it's not a uniform mount. Give me just a second. going to show you what spatial filtering is all about. You got your laser? Oh, thank you. Also, while you're all here, I'll demonstrate the technique for aligning the pinhole, because it is a technique and it is a pain. Okay, laser. Does it work? Yes. Oh, look at that, I got a target already. All right. Matter of fact, I'm gonna center it. That's right. Okay. One more thing. This is the spatial filter. Okay. By the way, when you're doing this, always want to make sure
Everyone's going to swap their defense out for all of our.
you always want to make sure that little off axis here, so that's okay. Everything is tight. I've had students in the lab who don't tighten this down, and they're like trying to align the thing, and the laser's going like this. You know, it's like, well, how about
It takes out one of your students.
It takes out one of the students, but also you're never going to align anything if everything's moving. So you figure out, like it did in the video, align the thing, check the height, and then lock it down. Okay, everything in optics is tight, precise, bolted down. Okay, it's the way it is. So if I put this in here, at just the heights of those through the center of the lens. Tweak this a little bit. Old eyes. There you go. Yeah, it's on the, you can't even see it because the, it's actually over here. Okay. Okay, remember I said this is a good beam, this is a crappy beam? Okay, this is what that beam looks like. Let me turn the lights off so you can see this. Crappy is a technical term. Okay, so beam's coming out. See all those squiggly lines? Okay, there's one right there, it's a little interference pattern. All of this other garbage around here too, that is not a happy, clean beam. Okay? But I'm going to show you how to clean that beam. Get it nice and happy. Grab coffee from my hands today. Yeah. That always works. Yeah. Okay.
Give them a monster.
So you saw this as the pinhole filter, okay? Magnetic mount, okay, the number 25 goes on the outside, so I'm just gonna stick this to here, okay? And if that's all I did, it would drive you crazy to try to line that up, okay? You could sit here all day long, you know, trying to like get that pinhole lined up. You're never gonna get any light coming through this thing. However, there is a technique. So, I know you can't see it from where you are, but the lens here that I have is about a centimeter or so away from that pinhole. Okay? At the end of the day, it needs to be about 1 or 2 millimeters away from that. Okay? But when you start out, if you move the thing back, that means the beam's going to spread out as it covers that hole. And if it spreads out enough, it gives you enough so if you look through the other side, you can actually see a little spot of light coming through. So I can adjust. I can adjust it until I can see it. And I can actually show you that. Just give me a mirror. Now, sometimes in optics, things don't have to be expensive. I find that these little like Maybelline makeup mirrors that you get at the dollar store make really good auto-collimated mirrors. So I'm just going to show you this. I don't know if you can see the light coming through this. There's like a little spot of light.
Yeah.
Yeah, just so you can, I know you can see it, but you guys might not be able to. So you can see the light coming through. And Ollie, can you kill the lights over there? Well, once you can see the spot of light, then you can start moving the beam. Actually, you can see a little bit of it coming through there. You can start moving your beam closer and closer. This is locked here. Towards the focal point. And if you notice, I don't know if you can see that, Earl, but
Yeah.
it's going to get a little
I
dark.
can see it on the back.
You can see it on the back? Okay. You know, so you're moving the lens closer and closer to the pinhole. And as you do it, periodically, you just kind of tweak the X and Y. Okay, like right about there, it's a little brighter. So it's not, and then as you get closer and closer, you're going to notice that the beam starts to jog off axis, but it will start to get brighter because the light is more light's going through the center of that. But you're going to see like a halo around that. I don't know if you can see those rings. Okay. And the closer you get, brighter it's going to get. Starting to look like a bullseye.
Oh, yeah.
Yeah. So every couple turns, you got to go back and recenter it. But that bullseye, by the way, anybody know what that is?
Related to Poisson's?
Exactly, yeah. The bullseye basically is you got a really small hole, light's going through that little round hole, and it's actually bending around the opening. And because this light is coherent laser light, as it bends, it actually interferes with itself. And where you see the dark spot, that's light that's arrived at that screen that is out of phase. Okay, some of the light came through the center, some is going off axis, and where it gets there, and there's a 180-degree phase shift between the beams of light, then you get a dark spot.
It is getting brighter.
It's getting brighter. So what you're going to see when you get right up on it, all of those rings are going to start collapsing into the center. And the closer you get, the more sensitive it gets too. It's going to start collapsing into the center of that spot. We're almost there. Again, this is why laser techs get big bucks. It's for patience. It's for patience. Almost. It's just like, okay, you see that other ring just kind of collapsed into the center. There we go. Not bad. Okay, so this is what we call a clean beam of light. Okay, clean beam of light means, you look at the lines on the paper, not the lines on the beam there, but there's no more of those little patterns, no more of that interference, no more dirty light coming through there. Okay, once you've done this, then you can collimate that beam with a second lens, okay, straighten it out, and well, I think I have one of the lens up here. Thank you. Oh, whatever. So, I mean, I could put another lens here, and I can collimate that, and I can straighten it back out, and you'd have a nice, straight, clean beam of light, okay, without interference in it. The dirty pattern there is basically called interference. Interference noise, whatever you want to call it, diffractive noise. So this is what we're going to be doing in lab today. If I had a second lens and I put it here, I would put it where I approximate where the focal point would be, and I take my Maybelline mirror, okay, put a little index card off axis, and then reflect it back there until it comes right down to the spot again, and you'd be fairly collimated there. Okay. Thank you, Bob. Oh, there it is. Okay. Here's my lens. Actually, let me try to do that really quick. 3 minutes. I can show you the auto-collimation method. So, I have this lens, I'm not sure, it says that's this has 100 centimeter focal length, which is a little too long for the table there. I'll try this. I'm not sure what this is, but let's show you. So, I'm not sure what the focal length of this lens is, but I'm collecting that light and, hold on, I need a taller. I'm getting my exercise. Bring it back. All right.
It should probably go higher. Yeah.
It's probably like
That's
that. Just enough to see.
pretty close to center there.
Yeah. So if you see the spot here, actually that's not bad. I'm just off a little bit there.
Yeah.
I adjust this just a little bit. It's growing a little bit. But this is where you would use your shear plate interferometer. If take one of these guys, and I will do it so hopefully you guys can see. Try to do this. So you get the right spot. Normally around a bench, this is mounted in a post. Thanks, you'll line it up. But, yeah, I'm not gonna be able to do this here with this, but it needs to be stationary. But you can see that, you know, as I adjust the position of this lens, that spot is actually fairly collimated there. It could be tweaked a little bit more, but we did collect that light and straighten it out. So if I had a longer focal length lens, the light would have more time to diverge and I can make a bigger beam. Of course, the lens itself would have to be physically bigger to collect it all, but we're going to play with that in the lab. So, all right, everybody has an exam? Who doesn't have an exam? Everybody's good, okay. So, for those of you who have lab, give me 15 minutes to set it up. Don't forget, tomorrow, if you're interested in going on that field